Okay, class, I'd like to do a short video on hypothesis testing. So, what we're going to talk about, the steps in hypothesis testing, the traditional model, then we're going to look at like a z-test for a mean, t-test for a mean, z-test for a proportion, chi-square test for variance, or standard deviation, and then that's kind of like discrete variables, categorical data. We'll use a chi-square test, and it's called a goodness of fit test. And then we'll look at other type of tests, and then we'll talk about some correlations and regression analysis in the next video. And with some of the other like ANOVAs, we'll be comparing the means of not just two groups, or splitting one group into two parts and looking at the mean differences. We'll actually be able to look at the mean differences between groups and within groups for multiple groups, for two or more, when we'll use what's called an ANOVA, and that's called an analysis of variance. And then we're going to look at different types of topics regarding hypothesis testing. Now, hypothesis testing, we're going to learn the definitions for hypothesis testing. We're going to know what a null hypothesis is and an alternative hypothesis. We're going to find critical values, and I'll explain in detail what a critical value is. And then we're going to use what's called the 5-step method for hypothesis testing. We're going to test means when we know what the standard deviation is. And we're going to test means when we do not know what the standard deviation is using a student's t-test. When we're using a student's t-test, basically we're just comparing the means of two groups or two means, and it could be the same group. That's going to be independent samples t-test or dependent samples t-test. We're going to test the proportions using a z-test. We already know what a z-distribution is, and we know what z-scores are. So now we have what's called a z-distribution or a z-test hypothesis. Now we can only use a z-test when we know our population parameters are normal. And usually when we get up to a sample size of 30, then we can use a z-test. However, researchers usually don't have an opportunity to get groups of 30 or larger, and they're forced to use a student's t-test. Now we're going to use what's called degrees of freedom within these smaller samples, and when we use different statistical methods like the ANOVA and like the chi-square, we're going to be dealing with degrees of freedom. So we'll talk about that. I could talk. We could have like several classes just on degrees of freedom and what that is. We're going to test the variances or standard deviations using the chi-square test for goodness of fit. And like I say, we're going to be using categorical data for that. And then basically we're going to look at expected outcomes and outcomes that we observe naturally in our environment. Then we're going to test the hypothesis using what's called confidence intervals. The chapter before this one talked about confidence intervals. I just wanted to integrate the two together. And then we're going to explain the relationship between a type 1 and a type 2 error and the power of a test. Now, a type 1 error is when a researcher reports the findings and they say, well, these findings are significantly, statistically significant, or there are significant differences between the means that I have studied. If a researcher reports the findings and he's reporting the findings wrong, he made a type 1 error. Now, a type 2 error is called a beta error. The type 1 is called an alpha error. The type 2 is called a beta error. Now, when we have beta minus 1, we associate that with the power of the test, and that's where our confidence intervals are going to come into play and things like that, because I can be 95% confident or 99% confident that I am reporting in my results the true outcome, that I'm 99% confident that these findings are true. So if I'm reporting that, that means that there is a 1% chance. If I'm 99% confident, there's a 1% chance that I can make a type 1 error. If I am 95% confident, then there's a 5% chance that I could make a type 1 error. If I'm 68% confident, then there's more room for me making a type 1 error. Nobody uses a 68% confidence interval. You know, in the social sciences, we always use an alpha level, like a type 1 error, the alpha error. We always use an alpha level of 0.05, which means that 5 times out of 100, I could have made a mistake. But nobody's going to know that except the great statistician in the sky. So I'm just telling people that 95% of the time, I'm going to be reporting the real, true results, and there's a 5% chance that these results are not accurate. 3 methods used to test a hypothesis. The traditional method, and that's basically what's called a critical value method, and I'll talk to you about that. And then the P method value. There's a lot of, I'd say, misunderstanding about the P-level method. Now, if you're reading a journal article and you're trying to get through all the statistics and all that stuff and it's making no sense, you can always go to the P-value and just look at the table and find out if the P-value, if there's significance in the study or not. Because the P-value is going to tell you, P just means probability. What is the probability of making a type 1 error? So if the P-value is less than 5%, and it will tell you that in the research, P is less than 0.05, then there's 95% of the researchers' findings, you know, that I can be confident that I'm reporting the true results, that there's no error in my results. But there's a 5% chance that these results are not true. And then, of course, the confidence interval, and going kind of rewinding a little bit back to what's called the confidence interval method, and the I'll think of it in a minute, but it's in the previous chapter. We're going to take samples and samples and samples, and we know that we're getting the true distribution of scores with more samples that we take. And we can be confident that if we take many samples, that we're going to basically find the true population. So if I take a sample from a population, I know that I'm 68% confident that the findings will be from -1 standard deviation to +1 standard deviation. We call it plus and minus 1 standard deviation of that population range. Then if I'm 95% confident that I draw a sample from a population, I can say that if I'm 95% confident, then my sample is going to lie somewhere between plus and minus 2 standard deviations. Then if I'm 99% confident that that a sample that I pull is going to fall in that range, then that sample is going to be somewhere between plus and minus 3 standard deviations from the mean. So that's what these confidence intervals will do. We're confident at some level, it's going to be 68, 95, or 99, that we're reporting the true findings. A statistical hypothesis. Remember from probably high school or junior high, we learned that a hypothesis is an educated guess. So basically, we're taking an educated guess based on statistical procedures. And the statistical procedures are, based on scientific statistics. So a statistical hypothesis is conjecture about a population parameter. Now we're talking about populations. This conjecture may or may not be true based on the level of confidence. So we have what's called a null hypothesis, and the word null means not. There's nothing, zero, zilch. So the null hypothesis is symbolized by H naught or HO. And this is a statistical hypothesis that states that there is no difference between parameters or values and means. So if I've got two groups that I'm trying to compare the means to, I've got group 1 and group 2, and I state my null hypothesis, what I'm going to do is state that there is no difference between those two means. So if I am working with a group of troubled youth who are having behavioral problems, and then I compare them to a group of youth, their peers, who are not having trouble, I may want those means to be the same. No difference after treatment. Then I could have some kind of study to where I have people with low self-esteem, and I know what normal self-esteem is, and the people who have low self-esteem, I want to get them back up to a level where they're having normal self-esteem. So those means would be equal at the end of the study. So it's not always a bad thing to have a null hypothesis. But in most cases, we're trying to find significant statistical differences between means, and I'll talk to you about what that is. So no difference if we're talking about the null hypothesis.